In this e-tutorial, we see the basic concepts to create assemblies in the program. We load a model including a solid. It appears as a solid type entity with the related context menu, similar to the one of other entities, with move copy, delete, and so on. Suppose this is our new assembly and we want to create a component of local type. Local because we must describe parts that must be designed directly inside the assembly and make sense just in that assembly and not in other ones. We gave it a name, and the local component icon is displayed, clicking which a context menu appears with commands associated to the component: set current, make X-reference with the same name, replace, and so on. Now we make the component become an external reference, that is, its description is written to a file external to the assembly. We keep the same name and save, so it has become an external E3 file. Clicking its icon and displaying properties, in the Component tab appear name, file name, and a series of flags, read-only and local copy. The context menu includes make X-reference, not shown now anymore as the component has already become an X-reference, open X-reference, we can open it, replace, and derive and replace. We need external references just because in some situations, as this one for instance, we believe the component is useful in other assemblies as well. Let's now see how to insert the external reference in a new model, an empty one. Insert, Component, X-reference. We insert the component just created, CL1_lock. It's exactly the component we previously saved in a new model. We position it by a click, and we can make a feature on it. How? Setting the component as current and performing the feature. For instance, a hole of this type, diameter 1, and so on. And we confirm. Then, right-click, reset current component, that is, go back to model level, and we rebuild the model. The feature we made is inside the component. Saving the assembly, we save also the part which, being an external reference, will keep the whole in other assemblies as well upon uploading. Wishing to make features outside the component, making sense only inside this assembly, we don't apply set current and make another hole on the part setting assembling feature, and the hole we made in the history tree is outside the component. We have two basic ways to create assemblies, bottom-up and top-down. Let's see bottom-up first. We close without saving changes and start with a new model, inserting components with the bottom-up method. That is, we already have some components previously created, possibly in the company archive, and we insert them in the assembly, so components created externally, then inserted in the assembly. We insert the first external reference component, cleavize. Important parts upon insertion keep the position they had with respect to the work plane upon saving. In fact, activating the work plane by W from the keyboard, we see how the part was positioned with respect to the work plane. Let's now insert another part, a rod. We place it by a click and perform the first mating by solid mating. So we select the object to be positioned and the reference one. In this case, the program shows the coaxial entities. As more options, we don't use deferred and symbolic references only. Deferred performs mating after inserting the different matings between the objects. The other restricts peak to symbolic references. We use simple mode, one mating at a time, while inferred calculates all possible matings between the objects. We place the rod. The model structure displays the mating including coaxiality. Even these can be redefined anyway. Clicking on it, we can see the two coaxial elements. OK. Let's now insert another mating in abutment in coincidence. We set visualization to shaded view plus boundaries to see better the bottom faces. Then, again, we apply the solid mating command, select the bottom face of the rod, and a plane face of clevice. In the preview, the rod will be oriented in the opposite direction. For coincidence, we must also consider the vectors perpendicular to the faces involved. Alignment was set to anti-align, while with align, the rod is in the desired direction. OK. Fit view to see better our object. And let's insert another external reference component. Clevice add, insert component XReference, placing the head in order to facilitate the mating. We position the head on the rod in vertical direction, but instead of simple mode, we select inferred, which means setting both coaxiality and coincidence, that is, all the constraints, all the matings that can be activated with these parts are activated. With simple, in fact, a tooltip with a single constraint is displayed, as now, while setting inferred, the tooltip shows both constraints, coaxiality and coincidence. We confirm by a click, and watching the mating just inserted in the history tree, both coaxiality and coincidence are displayed. We added two types of constraint by a single mating. Now we insert the last component, a pin. Insert component XReference is a usual pass. Clevice pin, always with the inferred option. OK. We position the pin and enlarge the bottom area. Keeping inferred, a mating with constraints of coaxiality and coincidence is automatically inserted. Coincidence with the face of the initial clevice and coaxiality with respect to the holes. OK. This is the bottom-up approach. We already have our components and use them to create the assembly, while with top-down, we build up each new component directly in the assembly file using other geometric elements and components already present. OK. Let's view the different types of mating. Working again at the mating of the rod on the clevice component, we can even redefine an offset. Previously, we had left it to 0, so in the history tree we just add coaxiality and coincidence in the related mating. All matings are elements with the history in the mode extractor, so redefine the mating in coincidence, we can enter an offset value, for instance 10. So the history tree displays an offset because it's no more equal to 0. To retrieve the value from an existing element, we can enable the adaptive measure, where we are asked if this value must be equal to the minimum distance between something that we are going to indicate to a length, a radius, and so on. We ask that the length is equal to the one of the edge we indicated, so we associated the offset to a measure of the assembly components, and we can now save the assembly without saving the component changes.